Hello, let us go forward with our lecture. And so the second little French theorem is the theorem due to Michel Rolle. And so I immediately go to that theorem. So we have a theorem by Michel Rolle. We are in the 17th century, so before the differential calculus and before the notion of derivative. So the following theorem is a reinterpretation of what Michel Rolle actually wrote. And the theorem is the following. You have a function which is defined on a closed and bounded interval. This time the fact that it is closed is important. Okay. In the Fermat theorem it was not, but here it is important. Then f continuous on AB, closed, and f differentiable in AB open, because we define derivative only for internal points. Then, and moreover, there is another hypothesis, which is that f of A is equal to f of B. So at the extremes of the interval of definition, the function f takes the same value. Then, the conclusion, the thesis of the theorem, then there exists C in AB, open, such that f prime of C is equal to 0. Okay, this is quite easy to understand, because here consider an interval AB here. So this is not a proof, this is just a picture, A, B. Then here you have f of A, which is equal to f of B, and then the function is continuous, so f of A is equal to f of B, and now see that what happens is that there is at least one point where the derivative is equal to 0. You can see it also kinematically. If you have to move from a certain level and then arrive at the same level, so move from a certain point and arrive at the same point, sooner or later you have to inverse your motion. This can happen also many times. Proof, be careful of the proof, because it is a very nice proof. I like this proof very much. It is extremely clever, extremely simple. There are no computation, but it is pure reasoning, pure logic, and the argument must be put in the correct order. Okay, so this is the proof. The first thing that one has to observe is that since f is continuous on AB, which is closed and bounded, by Weierstrass theorem, it follows that there exists an absolute maximum point x bar and an absolute minimum point x tilde. Now, we see whether at least one of these 2 points falls inside the interval. If it falls inside the interval, then f is differentiable at that point, and by Fermat theorem we will have that f prime is equal to 0. So we have to distinguish various cases. First, let us suppose that the absolute maximum point x bar falls inside the interval. Then, by Fermat, f prime of x bar is equal to 0. Second, suppose that x bar is not inside the interval, so suppose x bar is equal to a. Then f of a is the maximum of f of x for x in AB. Okay. Now let us look for the minimum. There are two possibilities. First, x tilde is equal to b. Then f of b is equal to the minimum of f in AB. But by hypothesis, f of b is equal to f of a. And f of a is, as we showed here, the maximum of f. So the conclusion is that the maximum is equal to the minimum, and if the maximum equals the minimum, then the function must be a constant. And if f is a constant, then f prime is equal to 0, is identical equal to 0 in the whole interval AB. Okay? Then there is the second possibility, which is x tilde is not b, so 2b, second possibility inside the second option. So x tilde is inside AB. Then, by Fermat, f prime of x tilde is equal to 0. End of the proof. This is very clean and very beautiful theorem, and however, when I ask it at oral exam, it is extremely rare. It is extremely unlikely that this theorem is described in the correct way. So let me comment a bit on this theorem. The first comment is the following. First, so f continuous on AB is a necessary condition, necessary hypothesis. Indeed, let us consider the following example. F from 0, 1 to r, f of x is equal to x in 0, 1, open at 1, 0 for x equal to 1, and here the function is this, 0, 1, but at x equal to 1 the function has 1, so even though f is differentiable, we have here that f is differentiable. Is differentiable in all internal points of 0, 1. Moreover, f of 0 is equal to f of 1, which is equal to 0. Then f continuous at 0, 1, but not at the border, f prime of x is equal to 1 for every x in 0, 1. So there is no c in 0, 1 where the derivative vanishes. Okay? So the hypothesis of continuity also at the border, at the boundary of the interval, is necessary. Second, this is the first comment, and the second comment is f differentiable again in the whole open interval in AB is a necessary hypothesis. Indeed, consider f from minus 1, 1 to r, for instance, and this is just the absolute value, and you know that f is continuous. In the whole closed interval minus 1, 1, f is differentiable in minus 1, 1, minus 0. F of minus 1 is equal to f of 1 is equal to 1. And f not differentiable at 0, but there is no c in 0, 1 such that f prime of c is equal to 0, since f prime of x is equal to minus 1 in minus 1, 0, and is equal to 1 in 0, 1. So it is never 0. And third, and this is probably the most stupid thing here, the hypothesis f of A equals f of B is necessary too. And again, let me give you the example. Here we have f from minus 1, 1 to r, f of x is equal to x. This is continuous in minus 1, 1, differentiable in minus 1, 1 open, and of course f of minus 1 is different from f of 1, because f of minus 1 is minus 1, this is 1. F prime of x is equal to 1 for every x in minus 1, 1. So again, there is no c in minus 1, 1 such that f prime of c is equal to 0. So here, through counterexamples, we verified that all hypotheses here, or hypotheses here, are really necessary. We have to keep them. And moreover, for a Rolle theorem, we have plenty of exercise, for instance, at the exam and so on. And a typical exercise is the following. So you have like in your test you have a multiple choice question like the following. You have the function f of x, which is typically a polynomial, x minus 1 to the square, x plus 1, x minus 6, for instance. And then you have this 3 possibility. At the exam you will have 5, but just to simplify the reasoning, A says f prime of x has no zeros in minus 1, 6. B, f prime of x has exactly 2 zeros in the interval minus 1, 6. C, no one of the others. And sorry, there is another one. D, f prime of x has at least 3 zeros. Okay. And so let us see what happens here. The point is that we know, okay, the trick is the following. We know the zeros not of f, which are the subject of the questions, but of f prime. Oh, sorry, not of f prime, which is the subject, but of f. Okay, so here you have the point minus 1, 1, and 6. And look at the signs of this. X plus 1 is positive after minus 1, and before it is negative, so signs here are minus and plus. And moreover, x minus 6 is positive after 6, and of course it is 0 at point 6, like x plus 1 is 0 at the point minus 1. And the last is x minus 1 to the square, which is always positive except at the point 1, where it is exactly 0. So here you have as signs, here you have plus and then minus here in the interval of interest, and then plus. So it is always negative, and you see why. You see that here the function passes through minus 1. Then 1 is a double root of the polynomial, so function does like that, and so on. However, there are 3 points where the function is equal to 0, and here you can apply Rolle's theorem in the first interval minus 1, 1, and so you get that there is 1 point where the derivative is 0. Then apply Rolle's theorem here from 1 to 6, and here again you have another point where the derivative is equal to 0. So you can say, just applying, so I write you here, Rolle says there exists an x1 in minus 1, 1, where f prime of x1 is equal to 0. And there exists an x2 in minus 1, 1, in 1, 6, where f prime of x2 is equal to 0. Okay, everything here is very simple, very clear, and this is just using only the location of the zeros. This is just what Rolle says. But you see immediately that among the answers, there is no answer which is good. We can say from here that there are at least 2 zeros of f prime, but here there are other possibilities, either no zeros or 2 zeros, exactly 2 zeros, and we don't know what happens outside the interval, and then at least 3 zeros. So here you should, this should suggest you that there must be another 0, and so if you just see the picture, or do a picture like that, you see that there is another 0 here, which is 1. But 1 so x3 is equal to 1 is 0 for the derivative for f prime 2. This is easily seen by the picture. So you have many possibilities by the picture, or noting, remarking that f is non-positive in minus 1, 6, so that f of 1 equal to 0 must be a local maximum, and since it is differentiable by Fermat, you have f prime of 1 is equal to 0, or by direct computation. Seems to be long, but it is not long. Take the function here. Since here you have a square, it is clear that when you differentiate and you use Leibniz formula, a factor x minus 1 appears at every term. So you have f prime of x is equal to 2 x minus 1, x plus 1, x minus 6, plus x minus 1 squared, x minus 6, because the derivative of x plus 1 is equal to 1, plus x minus 1 squared, x plus 1. So a factor x plus 1, x minus 1, appears in every term. So you immediately see that f prime of 1 is equal to 0. Then the correct answer is that there are at least 3 zeros of the derivative. And it was, if I remember well, the option D. Okay? This is all for Rolle theorem, so we go to next theorem and next video.